think I'm recording now. It seems like I am. Okay. Well, if I am, I am. If I'm not, I'm not. I'll do the best I can. All right. Now we're cooking, people. Sorry about the delay and my issues. So we're looking at what are known as differential rate laws. So let's kind of start walking through what that means exactly. All right. So what is a rate law exactly? When we say a differential rate law. Looks like my hair in the morning when I had hair. What a rate law does is it shows the relationship between the rate of reaction, oops, and the concentration of the reactants. And that's generally how they're expressed. So they're typically done in terms of the reactants. And so we're looking at a relationship between concentration and rate. Now we already know kind of a general idea that as the rate or as the concentration increases, the rate of the reaction also increases. But this is a lot more specific than that. We're going to look for an actual mathematical function that relates the two depending on the reaction system. So there's some basics that we have to understand about this. There's a general form that this will take on. So just like we did for the equilibrium stuff, we can write a generic reaction in which A and B, etc., however many reactants we have, go on to form products, whatever the products. It doesn't really matter because we're doing this from the frame of reference of the reactants anyway. So here's what you need to know. In general, every rate law problem starts the same. The rate of the reaction is going to be equal to some constant k. Notice this is a lowercase k because we're learning equilibrium at the same time at the other end, which is capital K, and they're not the same thing. And for every reactant, you're going to put in a term in which you put the concentration raised to some power x and then some power y, etc. Now here this is critically important. When we do equilibrium constants, the coefficients give us those exponents. But when we do rate laws, that's not necessarily the case. So the only way to get these exponents is through experimentation. We have to have data. And I'm going to show you what that looks like in a minute. Bottom line, this general form is how we start every problem. And what we have to have then is some table of data from which to figure out these exponents and then ultimately this rate constant. So let me define terms here. These are obviously the concentrations of the reactants. These exponents are called orders. And by order, I mean order of magnitude. Because if you think about it, if this power was, and usually there's 3 levels that we're going to typically see in these, although, again, we can see different values that I'm going to show you. But most of the time, these are going to be 0, 1, or 2. 0th, first, and second order. Think mathematically for a minute. If this were 0th order, what would that tell you about how the concentration of A affects the speed of the reaction? Think about it mathematically. If this was to the 0 power, what would happen to any number I put in here?
It equals 1?
Yeah. So doesn't that mean it would fall away, like it would have no effect? So when you look at 0th order, it really has telling me that that reactant has no effect on the reaction rate. That's the point of what 0th order is telling me. What if it was first order? What if this was raised to the first power? Then whatever I did to this concentration, that would happen to the rate. Meaning if I doubled this, this would double. If I tripled this, this would triple. So that's a first order effect And that's basically linear, right? It's direct. It's a direct relation, meaning if I double one, I double the other. And so what you can see is as I continue to increase the power to which this is raised, it continues to show an amplified effect on the concentration of that reactant on the rate of the reaction. So again, we have to determine this from experimental data, and it's that technique I'm going to focus on to teach you today. The last piece of this is this K. This is called the rate constant. You might see the term specific rate constant because, again, just like the equilibrium constant, this primarily depends on the temperature. But it's really interesting when you think about what it really tells us. Let me see if you can kind of already start to estimate. Because if you can conceptualize the mathematics that are implied here, here's what you should see. If I was comparing the difference between a reaction rate of, say, rusting versus an explosion, just picture what that means in terms of reaction rate. How would you assume the size of K would be in those cases? Like, if I compare this rate constant for a rusting reaction versus an explosion type reaction, how would K compare?
Rusting would most likely be lower than explosion because rusting happens slower than an explosion.
Yes. So really what the equilibrium constant is telling me is how fast is the reaction naturally. That's really what it's about. K is really telling me I'm going to say naturally, meaning like just by its nature. And so then the concentrations, that's right, Miriam, they're not the coefficients necessarily. That's right. So we're not going to assume they are. But what it's telling me is that K is primarily really telling me about the reaction itself, and then what we're saying is the concentrations can tweak the rate. Meaning, you know, rusting is not going to ever be as fast as an explosion, no matter how concentrated we make it, because its rate constant is much higher for the explosion. So we can tweak the rates with concentration, but we can't really overcome such huge differences in the nature of the reaction itself. I just wanted to make that clear. Oh, so I'm going to show you that, Miriam. I'm going to show you the process that we're going to use. That's the main thrust of the problems we're going to solve. Now, a word about units. Since rates are concentration over time, most of the time when we are calculating rates, the units are going to be either moles per liter per second or just molarity per second. And of course, if reactions are much slower, the time might be in other units like hours or days or years even, right? If it's a really slow reaction. But typically it's a concentration over a time. And so a lot of times on the AP exam, they're going to ask you for the units of the rate constant, okay? This is important. Equilibrium constants, we don't put units, but this one we do. And there's a real simple way to see how this has to work. Again, mathematical logic. We always want our final rate to be in molar per second units, let's say. This, then, is always going to have a time unit in the denominator, and then we're going to have to basically divide by as many molar units as we need to end up with just 1 molar left. In other words, if you look at the powers of this, right, like let's just assume for a minute that this was first order, and let's just forget that this is here, and let's just focus on one reactant. Well, this would have 1 unit of molarity, right? And so K's unit in that case would just be 1 over seconds. Because if this is molarity once, and I multiplied it by 1 over seconds, I'd get molarity per second. Well, what if this was squared? This molarity would be squared. Now I have too many molarities, so I'd have to put another molarity down here. What if this was cubed? Well, this would be cubed. Well, I got to get rid of 2 of those molarities. Do you see what keeps happening? When I look at the overall order, in other words, when I add up the x and y numbers that we're going to find, we call this the overall order of the reaction. So the equilibrium constant units will always follow this pattern. It'll be 1 over the molarity raised to the overall order. That's going to look like 0.0. Sorry. This is hard to write clearly in a small space. But the overall order minus 1, that's the power, right? We're always going to take all but 1 molarity unit away by dividing it out, and then times the time. So again, that's just a quick trick to help you always visualize what these units are going to look like. And I'll point this out as we're going, because I know it's hard to see until we see examples. So now I'm going to just do a series of examples that pretty much highlight how this works, and then what we can interpret from it. Sorry, let me write that a little bit better. Overall order minus 1. Any questions so far just about this general idea before I actually put together some problems? Okay, so let me grab a problem that's pretty straightforward because it only has 1 reactant, and I think that's a good place to start. Because if there's only 1 reactant, it should be easier theoretically, right? Theoretically. And then I can also introduce you to what does the data look like in these problems. So where's that first one I wanted? This one. Okay. Let me just copy this problem so I can write on it. Each time I do one of these, it should get easier and easier for you to see what I'm doing. Because, like I said, it's pretty straightforward once you get the hang of it. So we're given a table of data. And I'm going to highlight these words because this is the key words over here. Oh, sorry, I'm in the wrong mode. Initial rates. So the way these experiments work, it's called the initial rates method. And remember, initial rates mean, well, how fast is the reaction going at the beginning? So we can measure when the concentration is set up in this problem of the reactant, which is in this case this substance here, acetaldehyde, at 0.1 molar, immediately when the reaction starts, we find that its concentration here causes the rate to be about 0.085 moles per liter per second. Then we go to another concentration, and we say, okay, well, what did that do? Well, clearly it made the reaction faster, right? And again and again. And so we test different initial rates at different concentrations, and then we try to put this together to figure out what's the order. Let me show you how this looks. So that's what this first question is asking. Can we find the power to which the concentration is raised in formulating this rate law? So I would have started the rate law by saying rate equals some constant K times whatever reactants I have raised to some unknown power. Now they used M. I don't care if you use M, X, Y, whatever. It doesn't really matter to me. So what we have to do here is we have to ask ourselves what's going on with these numbers. So I'm going to set up a couple of different experiments and see what happens. So let's start with literally writing it out twice. And then I'm going to show you there's a quicker way to do it. So I always like to put the bigs over the smalls if I'm going to do ratios, just because the numbers are easier for me to be bigger than 1 than less than 1. No, the coefficients don't affect the concentration. What they affect is how much the concentration affects the rate. But let's see that evolve here. So let's write this equation twice. So the first time I'll do this, and the second time I'll do this. So let's say the second rate, rate 2, is equal to some K that we don't know, times the concentration that we do know raised to some power that we don't know. Oh, but we do know the rate, so I can actually put a number in here, right? Which is 0.34. And I'm going to write it as molarity per second. I know it says moles per liter per second. It's the same thing. Now, if we set up the same equation for, let's say, this first set of data, it looks similar, except now the rate is 0.085 molar per second. It's still the same rate constant. That's the whole point of it being a constant. It's not going to be changed by the different concentration. But now we did this at 0.1 molar, and the order is also the same. Now when you look at this, again, it's math now instead of chemistry. We have two equations and two unknowns. Isn't that enough to solve such a system? So you probably have various techniques for doing that. I'm going to show you what I think is the easiest one, and then I'll be able to generalize it so that when you see easier problems, you won't even have to go through this. What I'm going to do is get rid of one variable right away by dividing these two expressions. When I do this, the k is going to cancel out right away. And then when I do the math, here's what I find out. I get 0.34 divided by 0.085 comes out to 4. And then on this side, well, you should remember from math that when you divide and they're both to the same power, you can just make the whole expression to that, or that whole fraction to that power. Meaning what's really this can be reduced to on the right is 0.2 over 0.1, which is just 2, and it's raised to the x power. Right? Does that make sense, how I converted this fraction into this? Well, do we need any special technique to figure out what x must now be? Or can you tell just by looking at it how to solve this? What does x have to be based on what we just showed?
2.
Yeah. And so now we can write the general rate law, meaning the rate law for any temperature, because again, we haven't specified k yet. But now we know the order is 2. This is a second order effect, because what we're seeing is that when you double the concentration, the reaction goes 4 times faster. If you were to triple this concentration, 3 squared would give you a 9 times faster reaction. And so we see that this reaction is quite sensitive to the concentration of this reactant. We already knew it wasn't a 0 order reaction, because if this had been a 0 order reaction, what would be happening to the rate each time? Right?
Decrease.
I wouldn't say that. If it was 0th order, wouldn't this whole thing just fall away and the rate would equal k? What does it mean for the rate to equal k? It's
The same.
yes, it would stay constant. So for a 0th order reaction, the rate doesn't care what the concentration is. It just keeps going at the same pace. This is not that situation. And we can tell right away simply by the fact that the rate is in fact changing when the concentration is changing. But we can't just by looking see that it's first or second or third order. We have to go through this process. So that answers also the question, how do we get the order? Where does the number come from? It comes from an analysis of experimental data like this. What if the numbers aren't pretty? What if it wasn't obvious that x had to be 2? There's a really cool trick we can do. Logarithms. In other words, if you took the log base 10, or any log really, the same, it doesn't matter which base you use for this, but if you took the log of both sides, you would have gotten that the log of 4 equals x times the log of 2, right? And that's how you can solve for that unknown x. Now, did we have to in this case? No, because it was obvious. But I can generalize this. Anytime you want to find the order, you can always take the log of the ratio of the rates and divide it by the log of the ratio of the concentrations. That will automatically do what we just did by dividing these two equations. So
Sorry,
yeah.
can you show that on a calculator?
how to do this?
Yeah.
Sure. Let's do this very same problem. So all I would have had to do on my calculator, where'd it go? Oh, there it is. And it doesn't matter which two I pick, theoretically. So let's just pick two different experiments this time, right? Just for the sake of argument. So let's pick experiment, I'll do the first one and the last one, right? So if I took the log of 1.4 over 0.085, which are the rates, I'd get an answer. And if I divided that by the log of the concentrations, which is 0.4 over 0.1, right? So that's just 4, isn't it? And you see I get about 2, which is the order we expected.
That makes sense. Thank you.
You're welcome. So, yeah, so again, even if you're in a position where you don't know logs and theories of logs too much, you don't really need to be able to do anything more than really use the calculator once I show you, it's just really a function. But if you have more questions about the theory of logs, we can talk outside of class. All right. The next part of this question asks us to find the rate constant. How do we do that? Well, again, in theory, the rate constant is a constant. So no matter which set of data I pick, I should be able to solve and find k, because now I know the order. And if I pick any set of these data points and plug them in, I can solve for k, again being careful with my units. So let's just pick the first experiment. It doesn't matter which one I pick. This is 0.085 molarity units per second equals this k, and then in this case we're tying to this concentration, which is that molarity, and then squared. So all we have to do now is the math. And if you square this, you get 0.01, and if you divide it over, here's what happens. I got to be careful to make this look lowercase, otherwise I got to go out of my way to make a lowercase. So we would get 0.085 molar per second over 0.01 molar squared. And so what this would come out to is 8.5. And now again, watch the units. 1 molarity cancels 1, and this is 1 over seconds over molarity. So it's basically 1 over molarity seconds. Just like we said, since this is a second order reaction, it's 1 over 1 less than that molarity, meaning first order, like a power of 1, and then the seconds. So that answers A and B. And yeah.
Number B, do we have to like plug in another value rate to check our work, or is it just be the same?
No, it'll be within rounding, especially if it's obviously if it's experimental data, there's going to be some rounding error, or like a bit off for experimental error. But no, you don't have to do it more than once, unless it says find the average, and then you have to do all three and average them or whatever, But no, that's it. If you picked any set of data, you should get essentially the same answer. Now this last question says, can we apply this? And now that we can really write the entire rate law as what we could call the specific rate law, because now we have the actual specific rate constant for the temperature that we're working at. So now we have the whole thing fully worked out. Now it says, what's the initial rate at this concentration? Well, now we have a function, right? So we can just plug in a number here and output a number here, right? Now that's simple. And so we would just take 1.2 squared and multiply that by 8.5, and then our answer comes out to be about 12.2 molar per second. Wait a second here. Yeah, that makes sense. Because if you look at it, when we were at 0.4 molar, the rate was this high. We just made this concentration triple the amount. So it should be about 9 times as fast. And when you multiply 1.4 times 9, you get about 12 and change. So this pretty much shows us the characteristic of this type of problem. But that's only with one reactant. What if there's more than one? Then what do you do?
Before you move on,
Sure.
can I just ask, sorry, where did you get the 0.01 m squared for the denominator of k?
Oh, this is because when I plugged in 0.1 molar and it was squared.
Oh, okay, okay.
Any other questions? Oops, sorry. Keep moving this into the wrong space. All right, let's look at one that has more than one reactant. And I'm going to start again with what I think is a pretty simple one mathematically. So it's easy to kind of do in our heads. And we can focus more on what's different about the nature of the problem. So in this next one, I think it's one I just made up, like an A and B type. Oops, why does it do that to me? Jeez. Okay, let's do this to make it fit better. Did I miss part of the problem? I think I did. Oh no, this is a real problem, not a made up one. But the numbers are still pretty. What the? I love it. You know, it's like, of course, everything goes like goofy on me when I'm recording, right? Like, I'm trying to do like this whole smooth, like, you know, I'm cool and I'm on TV and I'm screwing it up left and right, of course. All right, so this is the reaction, and it says let's find the rate law and the rate constant. Now again, the big difference is that we have more than one reactant. And so I want to show you why this makes a difference, and yet it's really the same thing, just done more than once. So like if we take this reaction, we notice there's two reactants. So our rate law is going to start with the following. It's going to be some rate constant, but now I have to account for two different reactants. So let's do one and then the other. And as many reactants as I have is as many terms as I keep adding to the rate law, just the reactants. Now the problem here is if I try to do what I did last time, I have to pick numbers to plug in. But if I want to know each reactant's independent effect on the reaction, I can only change one at a time, right? In other words, I have to pick experiments where everything else is staying the same and I'm just fluctuating the one reactant's concentration to see if there's an effect. So you'll notice here I have 3 experiments. And you'll notice that going from the first experiment to the second, what's happening to the C2H2, which is this one? It's being held constant, right? But the concentration of hydrogen is doubling. So if there's an effect on the rate, it has to come from the hydrogen because this one isn't being changed. And that's what we look for. We're controlling our method to only let one reactant change at a time. So we have to pick pairs of experiments that vary one thing but not the other. Now in this case, look at how simple this is when the numbers are pretty. What is the factor by which we're changing the rate here? How many times bigger did the rate get?
Twice.
It's double. Yeah. And so what did we do to the concentration to get that effect? Didn't the hydrogen also double? But that's to the x power. So if we doubled the concentration and it's raised to some x power, we know it can't be 0, because if it was the 0th power, this would be 1 and the rate would not have changed. Could x be 1? Does first power make sense? Well, if I put a x equals 1 in here, then this is literally 2, which means this whole side will be multiplied by 2, which will make the rate twice as big. So we can see that the exponent here has to be 1. It can't be a 2 because this would square the effect and would make the rate 4 times. So that's what I'm looking at. I don't even have to go through the whole divide the equations or look at the logarithms. The numbers here are obvious. When the concentration doubled, the rate doubled. Therefore, it's a first order effect. So now we know that this is 1. Did that argument make sense to you, or did you want me to clarify anything on that? All right, then can you try doing the second argument? Tell me which experiments to pick to figure out if the second reactant has an effect and what effect it has. Okay, see you, Ryan. Any thoughts? Which experiments, first of all, would you pick to do the comparison, and how would you do it?
Wouldn't you pick the same ones that you used with the rates and the H2 because you're comparing the same things?
But I can't because I'm not changing this, right?
Oh, okay. So you'd pick the ones that does change.
So could I pick the second and the third because it changes here?
Yeah.
Will that work? Oh, but look carefully. I can't use this pair Y. Does anybody see why I can't use this one, this set? Well, isn't the hydrogen also changing?
Because one increases, but the other decreases.
Yeah, so it's hard to tell apart the effects if both things are changing. It's like trying to make soup better. And instead of just saying, let me add a little more salt and see what happens, you say, let's add salt, pepper, lemon. You don't know what made it better because you're changing everything at once. Every time you set up these problems, you have to always make sure you pick the experiments that only let the one variable change that you want to see. So in this case, and I saw somebody put this in the chat, if you pick experiment 1 and 3, now the hydrogen is being held constant, but we're changing the one we want to see the effect of. So now we're picking these two sets to figure out how this one affects the rate. Now let's look at the data. What are we doing to the concentration of this? Well, again, we're doubling it. And that's to the Y power. What's happening to the rate when we doubled it?
Remains
Stay the same.
Yeah, which is like saying the ratio is 1 to 1, right? It's like it's just not changing. So what must the exponent be for that to be the case, for there to be no effect?
0.
Yeah. So this is actually going to be 0 with order, which means the concentration of this reactant doesn't affect the rate. Now, why is that the case? We're going to learn more deeply about that later when we look at reaction mechanisms. But for now, that means our rate law literally just looks like this. The other term falls out because of the 0th power. And if we want to find the rate constant, once again, we can just plug in the data from any set of experiments and solve for K. Do you understand now the mechanics of how this is a fundamentally different problem in how we choose the experiments? Is that good? Let me put one up for y'all to try now on your own, and let's see how far you can get on your own. So let me put one up here. Okay, let's make it a little bit harder. And then I have one kind that's significantly harder. Hold on a second, I want to find a good one here. That's not the one I want, sorry. I'm going to pluck it off of this other document, not that one. Oh, I have too many things open. Okay, where's the ones I wanted? It's going to be one of these. We don't need to go for the throat on the first try, do we? This looks like fun. Yeah, this is a good one. Why not? This has 3 reactants. Oh my gosh, he's insane. All right, you all try that one. Same ideas, Same methods, you're just doing it more. Deduce the rate law is just another way of saying write the rate law, in case you're wondering. And if you're stuck on any part or not sure how to start, just put in the chat something, so I know how to guide you. This, by the way, says s to the -1, which is just another way of saying molarity per second. It's just hard to see it, so let me fix it. Okay, somebody's got a question here. Oops, get the question. Yeah, whatever. I mean, you can use any letter you want as a generic holding place. The things I would avoid are like O, because you're going to think it's a 0. I wouldn't use an I because it looks like a 1. But yeah, I mean, any letter. That's why sometimes you use M and N or whatever. It doesn't matter. If you want, you can type in either the chat or say, what you're getting as you go, and we can kind of check it as you go along, just so you don't feel like you're going through the whole thing wrong. I'll keep the chat open so I can monitor what you're putting up. Yeah, the order typically is going to be a whole number, but to be fair, it can be a fraction. I've seen orders of like 0.5. I've even seen negative orders. And all of that we can explain later when we get into, like I said, reaction mechanisms. But the most common values will be 0, 1, or 2. If you're getting like 1.3 or something, probably something's wrong, typically. And usually what's wrong is you're not picking the right pair of experiments. For Y, okay, let me check that one out. Did you use experiments 1 and 3 for that one, Miriam? Okay, so I'm going to try it right now. Actually, I don't even have to try it, because look at the rates. What is the rate doing between experiment 1 and 3? It's okay. I mean, that's what's the learning process. You don't have to feel bad. I mean, oops. That's weird. Huh. I'm gonna start closing some of these other. Sorry, I know I'm blocking your view, but just give me a second. There's just too many of these other windows open. That's slowing me down. Oh wait, did I close the wrong? Oh no, okay. Do 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 do. 90 things open here. Sure. So those answers look really good. So the context, I'm going to put up your results and make sure that we agree. So the rate is some constant. You said A is to the 0.5. B was to the 0, which I know falls out, but let's just explicitly write it. And C, you said, was 1. Are we in agreement? Or is anyone getting a different? Okay. They're the orders. Yeah, go ahead.
How did you find the orders for A, B, and C?
So that's what we've been kind of working through the last two problems. You have to pick appropriate experiments. So let's see for A, for example. Again, what we really want to do is make sure that A changes, but everything else stays the same. So if you look at the first two experiments, right? A is changing its concentration, but B and C are staying constant, so that they're not going to have an effect, and we can just study what A is doing to the system. Now, because the rates are not the same, we know it's not zeroth order, because changing A's concentration had an effect on how fast the reaction goes. The tricky part now is, how do we know what the value is? So the problem we're really solving is the ratio of the rates, which is dividing these two numbers. And here's another little trick. Because they're to the same, well, yeah, I can do this. Because they're to the same decimal point, it's the same thing as just putting 205 over 145, right, without the zeros. It's the same ratio, just to save yourself the headache. But A, the ratio of the concentrations is 0.368 over, and I guess I could have done the same thing here, left out the zeros because it's the same, 0.0184. But this is raised to some power, right, that we're looking for. So here's what you're doing now. You're saying, okay, if I take the 205 and divide it by the 145, I get a number of 1.41, this ratio. When I divide these two numbers, I get the number 2. So the problem we're now solving to get the order, we're saying 1.41 equals 2 to the x. And we're asking, what does x have to be? Now, this is weird looking, isn't it? It's like to the 0 doesn't work, to the first, to the second, to the... And that's why you can see that it's going to be a root here. Now, if that's not immediately obvious, you can use the logarithm trick, because if you take the log of both sides, you get this problem. Right? The x comes in front of the log. And then it looks like what I told you, the log of the ratio of the rates divided by the log of the ratio of the concentrations gives you the order, and you will find it's very close to 0.5. Kate, did you see what we did there?
Yeah, I see what you did.
Now, in order to, oh, you're welcome. In order to figure out the other ones, you do the same thing. It's just kind of a grind, but the most important step is using the right experiments. So if I want to test out B now, I have to look where B changes and nothing else does. So this is going to be too thick for me to draw with. I'll just use the red. So for B, 1 and 2 doesn't work, but 1 to 3 works, right? Because B is changing, but A and C are not. So when I use experiments 1 and 3, I could do a similar operation, but now I'm using appropriate experiments because I only want to see the effect of B on the rate. So I have to make sure the other variables are controlled. And now I can see again, B changes, but what does the rate do? Nothing. Yeah, that means it has to be zeroth order because a change in concentration did nothing to the rate. Miriam, I'm not sure about what you're saying. You said the rates are the same. Yes. And that's the point, is what I'm saying is the concentrations. So in other words, the concentrations are the input variable, right? That's my independent variable that I'm dealing with. The rates are the output or the dependent variable, and I'm looking for the effect on it. Oh, I did. Okay. Okay. And then again, if we do this one more time, we just have to pick the correct experiments. And in that case, the correct experiments would be, I believe, 1 and 4, because their C changes, but the other ones don't. So again, you're probably not going to ever see more than 3 reactants, but you could do this for 20 reactants, theoretically. You just keep controlling one at a time. And so if you're doing this in the lab, you're actually running experiments like this. You're changing one reactant concentration at a time. And we're going to look at something lab-like next time to kind of compare that to. All right. So from here then, do we need to go over the rest? I think this is like the hardest part, right? The main thing, because everything else is then just plugging in numbers, right? Like if I want to get the rate constant, I just pick one whole row, substitute in for everything I know, and do the math that's implied. Again, it's just weird with the units of K, because there's going to be like a strange like power, right? It's going to be like the negative 0.5 power of molarity or some weird thing. It really doesn't mean much. It's just to make the units work out for the whole thing. And then once I know K, I can just plug in givens and figure out the rate at that set of conditions. So how are we feeling about this kind of problem now? Before you answer that, let me show you what I put up. So again, link to this document. For now, not a key yet. But I have pretty much the second problem set. And I just assigned them all. Just say, try any ones you want. You don't have to do every single one, obviously. Some of them are going to be duplicates. And so what I'm challenging you to do is figure out what's best for you. So I'd start by at least reading through them. And then thinking about what they say. Let's do some of it together right now, and then let's just kind of get a swing and see what it's about. So check out this first question. Which of the changes would affect the value of the rate constant? Increasing the pressure of one of the components is not, no, it will not. It's a rate constant because the amounts don't affect it. Changing the temperature, however, does affect it. We haven't specified how yet, but it does cause a change in K. And this, I don't know if you'd be able to answer yet because we haven't gotten too far into catalysis, but actually, when you add a catalyst, it can also affect K. Because we had talked about how catalysts speed up reactions without being consumed. And part of what they do is they influence the activation energy, and later on we're going to see there's an equation that relates all these variables, that you can predict K based on temperature and activation energies of reactions. And since the catalyst affects the activation energy, then it can affect the value of K. So that was just like a what affects K type question. Again, this is not the equilibrium constant. This is the oh, sure, we can do that, and then we can verify it with Kirsten's number. So if we were going to calculate the rate constant in this one, again, I'll just pick the first row of data. It doesn't matter which I pick. So my initial rate is, can I just write it in scientific notation because it's annoying me? 10 to the minus fourth. That's in molar per second, equals K. Now I just have to take all the data from this first row. So 0.0184 to the 0.5 power, so it's just going to be square rooted. The B falls out, so I don't even have to worry about it because it's to the 0th. And then the C is 0.0141 molar. So mathematically, I take 1.45 times 10 to the minus 4th. I divide it by essentially the square root of 0.0184. And then I also divide it by the 0.0141. So when I do this, I'm getting 0.0758. And then I have to put the units in. So what did I do here? I had molar per second, and I divided it by molar to the 1.5. So just like x's work with exponents, what this would leave me for the unit is 1 over molar to the 0.5 seconds. I know that's a stupid looking unit, but that's just how it goes. So make sure that we agree and can get that answer. Or if we don't agree, make sure I didn't screw it up. Um, oh, that's okay. It is weird looking, and it's not really physically meaningful other than to make the units and the rest of the problem work out. That's really its only purpose. Okay. So from this position now, the question becomes, what's the best next step? I think, again, we can look at some of these problems together, or you can just look at them on your own. But I think it's worth at least reading through what they're asking before I let you kind of on your own. So this is telling me, just kind of testing whether you understand the way the orders work. Let's just do this one out loud together. You perform a series of experiments for this reaction and find the rate law has this form. Determine the value of x, meaning the order, in each of the following cases. There is no rate change when A is tripled. What would that imply?
X is 0.
Good. The rate increases by a factor of 9 when A is tripled.
X is 3.
No, that would give us a rate of 27 times, right? Because it would be 3 cubed. Right? When this is tripled and the output is 9 times bigger, you're saying 3 to the x equals 9. So squared, right?
Right.
Okay. And then it says when A is doubled, the rate increases by a factor of 8. Now what is x? 2 to the x equals 8. 2 times 2 times 2 is 3, right?
3.
3, okay. So that's what that question is getting at. This is exactly the kind of problem that we were just talking about. They're saying this reaction was studied at this temperature. The temperature doesn't really matter for our solution. It's just defining where the specific temperature was. And it gives us, again, some initial rates data. Why don't you guys try this one? Just do this one, this rate law, and go from there. You don't have to care about this, just defining how the rate was measured. So for our purposes, we're just going to say rate. As you're solving this, I'm going to point something out, and I think it appears somewhere in this assignment. It's one of the harder problems. I can even tell you which one later, but what makes it a harder problem is in some cases they can give you a set of data where they don't keep everything constant they're supposed to, and you have to figure out a way around that. So I don't know if I'm going to tell you that today. Maybe I'll let you encounter it. Okay, no problem. And then next time we can start there and just see that extra step. I just don't want to confuse that today because I think that will be too much. Yes, absolutely. Nothing new at this point. That was the lesson. If you need to go, go ahead. If you want to stick around and look at some problems, that's fine as well.
Thank you.
You're welcome. Have a good one.
Thank you. Bye.
Sure, bye-bye. I think I'm going to stop recording at this point too, just to save on my